Hello and welcome to the session number 6 of the Theory and Applications of Network Coding course. So in this session we will talk about advantage of using network coding techniques over using traditional techniques such as routing. The advantage that we will talk about will be in terms of maximum rate of throughput that will be achievable using network coding, and we will compare it to the throughput that will be achievable using traditional techniques. First, let us describe our performance metrics. So let h of n be the maximum number of packets that can be delivered from S to all terminals using n units. Again, here we're talking about multicast connection in which we want to send data from a single source to multiple terminals. And we want to send it over a network such that each link on this network can transmit one packet per time unit. And h of n will be number of packets that we can deliver using n time units. So the asymptotic maximum achievable rate is defined as the limit of hn divided by n when n goes to infinity. So when we have many rounds, how many packets can we deliver on average each round? So this will be our performance metrics, and this is what we will compare between the performance of network coding algorithms or techniques using network coding over traditional routing techniques. So formally, the coding advantage is defined by as h over h star, where h is a maximum achievable rate using any technique, including network coding, using network coding techniques, and h star is a maximum achievable rate using just traditional techniques such as routing or duplication of packets, but h star will be the rate achievable without using network coding. So h over h star will describe how much advantage we will gain by using the network coding techniques. As you remember, in the first part of this class we discussed the simple butterfly network. So for example, in this butterfly network, the maximum achievable rate using network coding is equal to 2. So we can deliver 2 packets per time unit to each terminal, T1 and T2. Without network coding, the maximum achievable rate will be only 1.5 messages per time unit. Therefore, the advantage of using network coding will be 2 over 1.5 or 4 over 3. So the natural question in this context is, can we construct an example, or can we construct a network for which coding advantage can be even larger than what we had in this simple butterfly network? And the answer is yes. It's possible to construct networks for which is much larger. For example, for this network depicted here, a coding advantage can be as large as h over 2 for a given parameter h. So let's see how this network is constructed. So again, this network is constructed for a given parameter h, and it has source node S, which will be connected to 2h intermediate nodes, and then any subset of size h of those intermediate nodes. For any subset of size h, we have a terminal connected to this subset. For example, if we pick those 3 nodes, it will be connected to terminal T1. For another subset, for example, if we pick the first node, the second node, and the fourth node, this will be connected to terminal T2, and so forth. So for each subset, for example, if we consider a subset of those 3 terminals, they will be connected to a node T6. For every subset, we have this terminal. And terminal will be connected to h intermediate nodes. So as we know that for multicast network, the maximum rate that can achievable is equal to a minimum cut that separates the source node and one of the terminals. So in this network, the rate achievable with network coding is equal to h. So what is rate achievable without network coding? So this purpose we need to show that it's limited, right? So what we'll show that basically what we can achieve without network coding is strictly less than 2. Therefore, the coding advantage is larger than h over 2. So now let us show that in this network, the rate achievable without using network coding is strictly less than 2. And the proof is by the way of contradiction. So suppose rate is 2 or more. So then the schema allows us to send 2n symbols over n routes, right? This is what implies if we assume that rate is 2 or more, then if we're using n rounds, we can send at least 2n symbols. So let's denote those symbols from B1 to B2n. And the first observation is that since capacity of each edge exactly 1, so the total amount of symbols the source can send is limited to 2n times h. And this follows from the fact that source has 2h outgoing links, and each link can send 1 packet per time round, or over n rounds we can send 2 times n times h packets. So now the next step is, suppose that each symbol that we're sending, symbol or packet, I will just use it interchangeably, it's the same thing. So suppose the set of intermediate nodes that receiving symbols I is denoted by ui. So the total number of symbols the source can send is equal to 2 times n times h, and each symbol will be delivered to a set of uis of nodes, or each symbol will be using size of uis transmissions out of those 2n times h transmissions that source can make, that source can deliver to intermediate nodes. Out of those 2n times h, uis will be using, size of uis will be using to deliver packet I. Therefore, if we're summing this up over all packets, the total number of sum of those sizes of ui over all packets that we're sending from 1 to 2n will be less or equal to 2 times n times h. Now, from averaging argument, this implies that there exists some value of I in which the size of ui is less than h. This is just from averaging argument, right? So if average size of ui is less than or equal to h, then there exists at least one I for which the size is less or equal to average. Again, suppose all of them greater than h, then they cannot sum up to 2n times h, because we have 2n of them. So let's consider this packet ui for which packet I for which ui is strictly equal to h. So this packet I will be delivered to a set of intermediate nodes which is strictly less than h. So it will suppose be delivered to those intermediate nodes, which in turn will forward it to terminals. Now, if the set to which this packet I is delivered is at most h, then there exists another set of size at least h for which this packet is not delivered. So, and then from the construction of this network, it follows there exists a terminal that connects to this set. Therefore, this terminal will not be able to receive this packet. And this is a contradiction that we can deliver 2n symbols to all of the terminals, right? So we show that one of the symbols cannot be delivered to one of the terminals. Therefore, the rate is bounded by 2, and coding advantage is greater or equal that h over 2. Now, the number of terminals is exponential in h, so we said the number of terminals is 2h choose h, which is roughly exponential in h. Therefore, the coding advantage is to some constant, right? So it's larger than, so it's big omega of the number of terminals. Number of terminals is equal to k, because h is equal to omega of log of k, where k is number of terminals. So we showed that for this particular network, the coding advantage is at least log k. So then, what natural question to ask is, can we do better? And the answer is yes. So there are some other constructions. For example, one constructions in which we show that coding advantage is square root of k. So for this network, the number of rates that we can be achievable with network coding is larger by square root of k than what we can achieve without network coding. If you want to, there is another work in which coding advantage is roughly square root of log n, slightly less than that, so it's log n divided by log n squared, all of the squared. This advantage is in terms of number of individual nodes in the network. However, those constructions are much more complicated and they out of scope for this particular course. Now let us consider the coding advantage in a more general case in which we have multiple unicast connections. So in this settings we have sets of source nodes Si, so from S1 to Sk, and set of destination nodes from T1 to Tk, such that destination node Ti is interested in the packet generated by source Si. So here, for example, destination Ti would be interested in the packet generated by source node S1, so suppose S1 generates packets A, so destination node T1 is interested in A. If S2 generates B, so destination node T2 is interested in B, and so forth. So for this particular network is constructed such that each terminal is connected to all other terminals, but not to the terminals that are actually interested in packets generated by this terminal. For example, S1 is connected to T2, T3 until Tk, but it's not connected to T1. And the same for other terminals. In addition, we have the special bottleneck link, which is connected to all sources and connected to all terminals. Now, suppose we don't use network coding. In this case, all those links that connect sources to other terminals are not really useful. Right? Because if source node S1 wants to deliver packet A to destination T1, it can only do it through this bottleneck link, right? So all those links that connect this source to other terminals are not useful for this particular purposes if we don't use network coding. Therefore, all of those K unicast connections, they share this bottleneck link. So the maximum rate that they can achieve is bounded by just one, right? Because this link can only transmit one packet per time unit. So this can be divided among connections, but total rate is just bounded by one. So without network coding, the rate is equal to 1. However, with network coding, each of those connections can deliver one packet per time unit. And this can be achieved by just using a simple combination. So for example, in this bottleneck link, it just combines those packets using, for example, just simple exclusive or just addition over a small field like JF2. Right, so in this case, for example, this node will transmit just a combination of all packets. And then each destination node will be able to decode the packets it needs, because it will receive a combination of all packets generated by all terminals through this link, and then it will receive all additional packets through those direct link from the source node, right? In this case, for example, this node will be able to decode A. And destination node T1 will be able to decode A. Destination node T2, again, it will receive combination of all packets through this bottleneck link, and will receive a copy of all packets other than B over those direct link from sources, so it will be able to decode packet B and so forth. So in this case, the coding advantage is equal to K, because the sum rate with the multicast will equal to K, because we have K unicast connections. Each connection can deliver one packet per time unit. So we see that coding advantage in this case is much larger than what we can achieve in case of multicast. So far we discussed coding advantage for directed networks, for multicast sessions, and for multiple unicast sessions. So let us consider other settings. So the first setting is a unicast connections. So unicast connections, we have a single source S and single destination node T. So for such connections, we know that maximum amount of information we can send is equal to minimum cut that separates S and T. But then from Maxwell min cut theorem, we know that number of disjoint paths that connects source and T is equal to minimum cut. Therefore, we can send information from S to T over disjoint paths And we can, by doing this, right, by sending information over this join path, we can achieve the capacity of this network. Therefore, the capacity can be achieved by just not using network coding, by using traditional techniques such as forwarding. So in such settings, network coding doesn't give you any advantage. Whatever can be achieved with network coding can be achieved without network coding by just routing. However, as we see later, if we not only interested in throughput but also in some other properties such as achieving robustness against edge failures, then network coding can give us advantage even if this case of unicast connections. So another settings for which network coding doesn't give any advantage for in terms of throughput is broadcast connections. So in broadcast connections, the source needs to send data to all nodes in the network. So every node in the network needs to decode original packets, or equivalently, each node on the network can be considered as a terminal node. So in this case, when we need to send data to all nodes in the network, all other nodes in the network coding doesn't give any advantage. So additional settings that we can consider is undirected networks, right? So far we focus on directed networks. In undirected networks, again, we don't have directions on links. They can be oriented in any way that we like. So we have more flexibility. In this case, what we know is that coding advantage is upper bounded by 2. And again, we will talk about this later in the course. So, which is different, right? It's much lower that we can achieve in directed networks. And lower bound, so we can show examples of network for which network coding has an advantage. We only have 8/7. So it's different again from directed networks. So another settings we can consider in undirected networks is multiple unicast settings. So in which we have an undirected network and we have multiple sources. And again, we have multiple unicast connections. So source S1 wants to deliver data to T1, S2 needs to deliver to T2, S3 to T3. So this case is actually open. So the conjecture that in undirected networks there is no advantage for network coding. However, this conjecture was verified for special networks such as bipartite planar graphs, but in general it's open and it's not known much about this, right? So it's believed that network coding will not give an advantage, but it's still an open research problem. Okay, thank you very much and see you at the next session.